So I'm going to talk to you today about why the challenges we face in scaling Moore's Law are unprecedented, not only technologically, but also in terms of market incentives and in terms of the institutional support to overcome the challenges that lie ahead. I'm going to argue that the scale of government support needed to overcome these challenges needs to be greater than even what you're going to see today. And I'm going to argue that the country that should be overcoming these challenges is the United States, not only for ourselves, but for the rest of the world. So, the first two-thirds of my talk draw from the dissertation of one of my students, Hassan Khan, who I had the honor of co-advising with industrial historian David Hounshell. The quality of the history that you're going to see is thanks to their incredible work. So the 40 years of incremental innovation along a dominant design that we see through Moore's Law from 1975 on forward, we'll talk about why I started 75 separately, is not only incredible technologically, it's also incredible in terms of its economic and social benefits. Dale Jorgensen at Harvard attributes 50% of economic growth in the United States and worldwide to the incremental advances in microprocessors during that period and the corresponding advances throughout the supply chain, up and down the supply chain and applications as well as equipment that led to this economic growth throughout the economy. The social and quality of life benefits are even harder to measure. The reason that these economic benefits accrue, economists call due to this technology being a general purpose technology. But unlike many people who talk about the next scaling technology with economic benefits is going to be biotech or this or that, it's actually very hard to achieve what's required to be a general purpose technology. You need ubiquitous application throughout the economy, like we see in microprocessors. You need technology dynamism, like the 18-month or every 2-year cadence of improvement that we see in microprocessors. And that improvement has to enable innovation complementarities in other applications up and down the supply chain throughout the economy. That's rare. Steam engines were one of the other examples that people attribute to having those qualities. And for a matter of fact, for that to go on for 40, or if you want to call it 50 years per Bill Chappell's notes, is incredible. So this started, this capability, out of Bell Labs and military seed funding. In 1947, Bell Labs invents the point contact transistor, and the bipolar junction transistor is invented by Shockley in 1948. Interestingly enough, an antitrust agreement forbid Bell at that time to manufacture these transistors beyond Bell. And Bell was forced to openly license and share, with oversight by the Department of Defense, for a matter of fact, what was the patents, the industrial recipes, and otherwise, by what became known as Ma Bell's cookbook. So quite different than how we might think of things today. Military agencies play a very important role at this time in funding particular R&D trajectories, in providing production facilities for early technologies, and as serving as an early and eager source of demand. By the 1960s, monolithic integrated circuits have emerged as the dominant design, really in overcoming the instability that was associated with the tyranny of numbers, people hand wire bonding together all these different devices. And by the late 60s already, civilian demand is outstripping the demand by the government. So what continues then for 40 years of industry-led, what we would call incremental innovation, really follows two blueprints that emerge in the 1970s. There's Gordon Moore. Now, he writes his 1965 paper, but Gordon Moore writes about drivers for density in his 1975 paper being die size, transistor shrinkage, and circuit cleverness, the ability to sort of reorganize the chip. And Dennard in 1974 writes about Dennard scaling and notes that in order to achieve that scaling or shrinkage, we have dimension, dopage, and voltage as parameters that we can tweak. And he even notes at that point in time the challenges that are going to emerge in terms of minimum gate, oxide thickness, interconnect resistance, and non-scaling subthreshold slopes. So as we proceed forward with Moore's Law during this period, collaborative institutions start to emerge across the economy. What we see here is on the y-axis, we have market share. On the x-axis, I have time. And you can see the US's share of the market kind of going down underneath Japan's share. So what happens in this period is in 1977, the Semiconductor Industry Association is formed to lobby on Japanese trade issues. In 1982, the Semiconductor Industry Association, or SIA, founds the Semiconductor Research Corporation, which is a fascinating program to fund, jointly with other government agencies and industry coming together, silicon integrated circuit research at universities at that time. In 1987, 14 SIA firms, the Semiconductor Research Corporation, and the Department of Defense, in particular DARPA, form Semitech. Now, Semitech is really focused on 1 to 3 year out equipment upgrading because we're worried that all the equipment is only being able to be made by Japan. By 1992, SIA and the SRC initiate the National Technology Roadmap for Semiconductors to coordinate research investments. By the time we've gotten to that point now, and we're moving into the mid-1990s, these collaborative institutions start to shift away from the concerns about Japan and toward concerns about technology capabilities. So NTRS study in 1994 finds a research funding gap for long-term research. And then around the end of the 1990s, we start to internationalize mapping with these collaborative institutions, mapping what's going on in the industry as a whole. So as we get to that internationalization period of the collaborative institutions and the industry, we also start to come into, by 1998 and going forward, we're going from Dennard scaling, and we're facing those limits pointed out by Dennard and others several decades earlier, and we're starting to go towards equivalent scaling. We're using other material innovations rather than the tweaking of voltage and dopage and otherwise. That equivalent scaling isn't cheap. You can see here that the revenues of industries are not keeping pace with the funding that they're having to put into R&D, and indeed R&D intensity is increasing over this period of time. You can see the exponential increase, and especially look at 2010 to 2012, it's sort of incredible. So despite this incredible amount of money being put into equivalent scaling, we're also not keeping pace already by 2004 in terms of performance. So central processing unit frequency projections, I find this slide put together by Hassan somewhat incredible. So you can see in 1997, we keep getting more optimistic in these various roadmaps about what we're going to be able to achieve in terms of frequency projections, and yet at that time, sort of CPU frequency that's the blue lines, is just staying constant. So we're not really making the progress that we're projecting in the roadmap. Now, it's not that people aren't paying attention at all. So you can see this is language from the various roadmaps matching the colors. And we go from 1997, there being some challenges funding long-term research beyond 2006, to by 2003, the Emerging Research Device chapter has become central to the ITRS roadmap, and the executive study summary talks about being concerned about the revolution looming ahead. There also is a lot starting to bubble up in terms of funding. The SRC by 1999 starts to have funding of beyond CMOS technologies, building on the DARPA Ultra program from the 1990s. And DARPA is also funding at this point in time beyond CMOS concepts, spintronics, molecular electronics, steep threshold devices, sub-threshold devices. So the National Nanotechnology Initiative, the industry really lobbies to get that launched. That's happening by 2001, so we've got activities going here. And likewise, by 2003, there's some very serious, quiet executive level conversations happening about what's about to happen. And for a matter of fact, in a closed-door meeting that we had access to in terms of the archives, in January 2004, the SIA Technology Committee, a group of executives come forward and they say, you know, to really solve this problem, we need $600 million a year, we think. And we think that this should be done in an industrial research institute. So this is actually from that planning meeting that led to the creation, instead of a $600 million a year institute, to the creation of the Nanoelectronics Research Initiative within the Semiconductor Research Corporation. And yet the Nanoelectronics Research Initiative is only being funded at $20 million a year. And in part, that's because the executives decide it's impractical. They don't see who's going to come up with this $600 million a year in funding. So by the late 2000s, the ITRS roadmaps are catching up, and they're talking to us about 3 competing trajectories going on in sort of the future of Moore's Law or beyond Moore's Law. The first one they note is more, that's what they call it, and this is essentially going forward with equivalent scaling. And in our paper on this topic, we add to this arguments like Lyserson's, that's misspelled, Charles Lyserson at MIT's paper on that there's plenty of room for the top. We're going to get advances through software, forget the silicon, it's all going to be okay. But you note that this is very expensive. We already talked about, maybe not on the software side, but on the equivalent scaling side. The second trajectory noted by the International Technology Roadmap for Semiconductors is what they call more than more. So this is functional diversification of semiconductor-based devices, integration of new sensors, electromechanical MEMS devices, and otherwise. And we add in our paper to this more than more trajectory systems firms bring chip design in-house, like Google's machine learning specific TPU technologies. And then the third trajectory that the ITRS notes is beyond CMOS, needing new devices or looking at new devices that are no longer in silicon, the spintronics, graphene, you choose your favorite option among, I think there's a point in time there where they talk about letting 1,000 flowers bloom early on in that work. So what's interesting about these 3 trajectories, and in part what leads to today's time period being unprecedented, is that this more than more trajectory is lucrative. This is highly lucrative, especially in the application-specific areas, and yet it reduces the general purpose nature of the hardware, and it also reduces the incentives for collaborative research. So the question that we face as we think about these 3 trajectories and what that may mean for us going forward is there a point in time at which more than more requires something other than today's silicon-based technologies? Do we have at some point in time that some new device, with new interconnect and new architectural capabilities across an entirely new platform are going to be needed? And how soon is that? Is that 10 years from now? Is that 30 years from now? When do the existing technologies run out for us continuing the capability of computational advance? And you could argue we don't need any more computational advance. I gave a talk at Stanford and someone told me that. And so, but it's probably not this audience. Anyways, if we're looking for our collaborative institutions to come forward and solve this problem, it's not likely. right? So you can see here, this is internal access we had to the Semiconductor Research Corporation's membership database. You can see membership declining since the mid-1990s. This is because of consolidation of the industry. This is because also of the failure of companies like Google or Microsoft or Facebook that are taking these application-specific directions to join. You likewise see the other institutions declining. Also, the equivalent scaling getting more expensive doesn't help. Semitech is absorbed into SUNY Albany in 2015. The ITRS support ends from SCRC and Semitech already in 2013. From SAIA, ITRS support ends in 15, and the publication ceases in 16. Now we've had some rebooting coming since then. So, is government going to solve our problem? This could be a second, or maybe it's not the collaborative institutions. It's maybe not, if we believe that we need a beyond CMOS or other capability eventually, this is also somewhat concerning when you look at how much money is going into this compared to what's gone into this in the past. So public funding for nanoelectronics plateaued in 2011 at $90 million a year. What's shocking about that, and that's not even focused just on beyond CMOS technologies or on a new form of computing that has quite a broad range, that's less than half of annual public funding for Semitech. Annual. So annually, in inflation-adjusted dollars, we were putting $200 million a year through DARPA into Semitech for 1 to 3 year out equipment upgrading to beat Japan. And right now, only $90 million a year is going into nanoelectronics. PCAST in 2017 recommends moonshots, but I would argue this is not the right organizational form. The scale of the problem and the coordination required across the stack making this a prize or moonshot deal rather challenging. And while we see new SRC programs in 2018, JUMP, co-funded by DARPA, NCORE, co-funded with NIST, again, the amount of funding is much, much less than even what we were putting into a much easier problem, equipment upgrading versus finding new basic science. So we would argue, and this is where we get off the I can promise you what the history says, and to what looking at the industry we believe is that there's a case for substantial US public funding. The magnitude of the social benefits to continuing computational advance are probably quite large, whether that be economic growth or social welfare. I expect we would like more computing capabilities going forward, not to mention the national security implications. The coordination required is with beyond CMOS and across the stack, if the existing institutions aren't taking this on, is quite significant. We see no reason not to believe the internal industry meeting that believed it needed $600 million per year. We would argue that probably that would have to come in terms of, because of the basic research components of some of this, about 90% from public research dollars and 70% from the Department of Defense of that 90%. In terms of organizational forms, maybe a research institute, like they proposed, although you would need academics and government PMs as key players and industry players across the computing stack, as well and coupled with semi-coordinated cross-agency activities. So we don't believe DARPA should be the only player. It already isn't. You've got activities in the DOE and NIST, but I was fortunate in my own work to have been only one of 2 people over time to have had inside access to looking at how DARPA works. And in that work, what stood out is the role that DARPA program managers and office directors play in orchestrating technology directions. So they come out of industry or academic positions for 3 to 5 years, and they are enabled to serve by flying across the country, finding out what everyone's doing, as connecting disconnected actors, and almost being a symphony director is the way often people on both sides of the table talk about this role. So when you're thinking about coordinating across the stack, that type of activity may be particularly important, both in teaming as well as in enabling the conversations that happen across here. And then to close off, since I am personally often most known for my work on looking at global manufacturing and the future of technology, I think we should end with the questions often most asked when we talk about this type. So we're talking about, where's $600 million a year going to come in order to look at this problem, if we believe that's the amount that should come for it. Is another country going to get there first? Maybe that's a reason we need to spend $600 million a year. Is there going to be all this money spent, and yet only for then whatever the next microprocessor is to be made abroad? I think if we think about this first question, will another country get there first? When you look at this case of microelectronics and microprocessors, I think the answer is probably not. China is just working towards their 14-nanometer facility. I think that's not really going to be a competitor. There's excellent activities happening with IMEC and otherwise in Europe, but I wouldn't argue that they are likely. I mean, the key players are here in the United States at this point in time. I do think what we need to worry about in terms of China or developing East Asia in general is how the manufacturing of microprocessors as commodities is driving down prices and would make it potentially harder to introduce new technologies in a market competitive way here. And so just to give you one example, this is work in optoelectronics and integrated circuits, and this is just, I know there's one activity here in integrated circuits among others in optoelectronics. So this red line is the old technology. This is actual data from across the industry, facility, plant floor level data. So that's the red line is the old discrete technology in a very, very high-end device, transceiver device produced in the United States. The blue line is the monolithically integrated device produced in the United States. And you can look at this in publication, but you can produce that old discrete device in developing East Asia for dramatically less money. So even though you have a size benefit of that monolithically integrated device, it turns out that that is stuck if you're entering the market with the same product, not able to compete from a cost perspective. That doesn't mean market performance with the developing East Asia discretest hand-assembled devices. And that creates challenges. So as we think about commodities driving down prices, and now we're having a government intervention, is what we're going to pay for going to stay here and be manufactured here? I would argue that it's most likely yes. And there's a preponderance of data that shows that in advanced material and process-based, very, very cutting-edge technologies, where manufacturing usually is still an art rather than a science. And the examples here, I'm just giving you a couple of them, range from early-stage pharmaceuticals through the electronic semiconductor industry in the early years, 40 years ago, through optoelectronics at the very high-end devices, the ones Huawei still can't make, as well as through additive manufacturing, that we're unable to separate manufacturing from the locus of the inventors. This doesn't mean after VLSI is introduced and so forth that we can't, but in the early years we can't. At the point that VLSI is introduced, you can. And so I would argue that the most likely outcome is that it will be made in the USA, demanded by the world. And for a matter of fact, when we think then about, okay, once it commoditizes, what should we do? It's not clear that we're going to have a device that's going to be able to have 40 or 50 years of scaling going forward. And so it might be a situation of running faster, always, to Bill's own words, than anyone else to keep creating the new thing, which keeps getting manufactured here. Whatever that new device and platform for information processing happens to be.